Sir William Bailey. Okay. So what I've done, y'all don't see this same view, but you should have 3 assignments open to you right now. One of them is the reading, it says what makes our solar system possible. One of them is the constructed response from yesterday because I had less than half the people turn it in. So if you wrote the stuff down, make sure that you end up submitting it. And if you didn't write the stuff down, go in and write it. It's just 2 questions and get it submitted before the end of the day today. We do have the multiple choice. I hope this isn't y'all and y'all are just getting in there and answering these questions. Because to be honest, the multiple choice is kind of difficult. Like I always thought that the grades would be better in these, and then every single year I do them, the grades are not. Which is why I'm going to go over it today and hopefully give you all the answers you need to finish the multiple choice assignment. So first off, let me just draw this on the board. That way I don't have to make a picture. In the Milky Way galaxy, if I did not already mention this, the Milky Way, there's 2 kind of ways that you can look at it. From above, you have like a center of the galaxy, and then the arms kind of spiral outward. So you have this nice like spiral kind of look to it. We, as a solar system and a sun and a planet, are probably like out here somewhere. We're not at the very edge. We're kind of like at the outer part, middle part of one of these arms. And so they ask you where we're at in the Milky Way galaxy. We are in one part of the arm of the Milky Way galaxy. If you're looking at it from the side, which I think is what the question asked, we're going to be kind of off to the side, out in the edge of one of the arms. Not in the center, not way up here or anything. We're going to be off to the side.
Does it spin?
Yes, it does spin. It takes a really long time to spin, and they actually ask you a question about that. And so maybe I'll be able to kind of explain that a little bit. For the people at home, this is my wonderful drawing of the Milky Way, and we are kind of over here off to the side of the Milky Way on one of the arms. So if they show you a picture of the Milky Way, we're going to be off to kind of like to the left. Left, right, none of this really matters in space, but there you go. I don't know. Don't worry about my YouTube channel. I ain't making no money off of it.
I subscribe.
You have 4 subscribers now.
So, what statement? So they ask about the inner planets and the outer planets. So remember, the inner planets are small and dense and rocky. The outer planets are large and not very dense and gaseous. So these are the gas giants. These are the rocky planets on the inside. Let's see, what else? Oh, my pages are sticking. Used to, you just lick your fingers and your pages come apart.
Just lick your
Not anymore. You don't lick your fingers, especially like at the grocery store. If y'all ever shop, you gotta like get the bags open for the produce. Can't lick your fingers anymore. That's just not a thing we do. So yeah, this question asks about the Milky Way rotating. And I don't know. It's not even gonna be in here. And basically, they're like, in 250 million years, will we be on the other side of the Milky Way? And the answer is no. We basically I don't know. It might be even like a trick question. In 250 million years, even if the galaxy turns around, we're still going to be in the same part of the Milky Way galaxy. So that's kind of the answer that they're looking for.
Taylor Rose, Cash Rickman, Esmeralda Rivera, Aaron Roberts, Colin Roberts, Natalie Roberts, Nathan Roberts, Emerson Robinson, Araceli Rodriguez, Daryl Rodriguez, Eduardo Rodriguez, Jessica Rodriguez, Jesus Rodriguez, Juliet Rodriguez.
Are they going to drug test the kids at home?
Oh, I was asking that. Yeah. I made a joke to one of the other online videos. I was like, at-home students, you need to go buy an at-home drug test and
No, they just
send it in to Mr. Warner.
Just urinate into an envelope.
Yeah, just send it in there. So they ask about. So remember we talked about Copernicus, and before Copernicus, we thought the Earth was the center of the solar system, and then Copernicus is like, no, it's the sun is the center of the solar system. We kind of thought the same thing at the beginning too. We thought that our solar system was like the center of the galaxy, and everything else moved around us. We know that that's not true now too. Not the galaxy. Not only are we not the center of the galaxy, our galaxy is not the center of the universe. We're just kind of off to the side in all levels. So they ask you about that. What is the age of our solar system? Does anybody remember the age of our solar system and the age of the universe?
It was like
13 billion years.
13 is the universe, and then our solar system would be younger. It's like 5 billion years, like 4.7, 4.6, yeah. So 5 billion years for the age of the universe. Or no, the age of our solar system, about like 13.7, 14 billion years for the age of the universe.
Which one's the oldest?
The universe would be older than our solar system.
No, I mean which planet is the oldest?
As far as planets, ages, all of them are going to be roughly the same. They all kind of formed in the same nebular formation.
Same few billion years.
So yeah, they might find that one is like slightly younger, but it's not going to be any reasonable amount of time. So in general, they all kind of formed together at the same time. So what is the hypothesis for how our solar system formed? That was kind of what we went over yesterday. It's going to be the nebular hypothesis. What phenomenon do scientists typically use to detect extrasolar planets? So what they talk about with that, and I will actually show you something real quick, probably on the board. So it's not in here. They talk about the nebular hypothesis, how our solar system formed. And then if you come to the bottom and you click next, it takes you to the next page, which is page 2. If you scroll down a little bit, the part that I highlighted yesterday talks about extrasolar planets. And what they're talking about here is, let's see, do they have a video of it? Our position in the Milky Way, video segment light years, no extrasolar planet videos. Okay, so let me actually draw this on the board because this is an interesting concept. I talked about the Doppler effect yesterday, right? I made the funny noise where I ran by and it's like a car going by you and it's like, yeah.
Wait, Gage wasn't here for that. So you got
Well, he'll be all right. I think he gets it. Yeah. So when you run by, and this will be for the online people too, if you're honking your horn and you're in a car and you're passing by somebody, they hear it like this. It's high pitched when they come towards you, and it's low pitched when you go by them. And so that is the Doppler effect. When you're going towards something, it's going to be compressing the sound waves or the light waves. And when you go away from something, it's stretching the sound waves or the light waves out. Now, how do we use that to find planets? Sometimes if there's a star, the planet crosses in between you and the star. So you get to see the star dim. But there's lots of planets going around stars that maybe go around it like this, where it never crosses in between us and the star. We'll never ever see it. So how do we know that that planet is there? How do we get to see that? The way we do that is it's actually due to gravity. And this is what they're kind of describing in that paragraph a little bit, the Doppler effect. When a planet, let's say there's a sun here, not a sun, but a star, and there's a planet, a pretty big planet over here with a lot of gravity, maybe like a Jupiter or a Saturn. As it orbits around the star, let me put little arrows. As it orbits around the star, it's going to pull the star with it. There's going to be a slight little movement of the star. And so at some points, this star is going to kind of be going around like this, just in a little circle. It may not even be like an actual circle. It might just be kind of like jiggling a little bit.
That planet's bigger than that star?
That's probably not. I didn't draw that accurately. Jeez, just give me a break. This isn't our class. Yes, this is the star, and the planet would be smaller, but I made it bigger for exaggerated effects. Planet. But the point is, if you have a big planet, it can actually pull the star around a little bit. So it's kind of like doing this circular jiggly motion in a way. Now, if we're way over here on the Earth and we're looking at this thing, there's sometimes the star will be headed away from us, and sometimes the star will be coming towards us. It's just slightly, just barely moving like that. But if we have a telescope that's sensitive enough to see it, we will see that Doppler shift towards the red and the blue section. And so I think they yes, this pull from the planet on the star causes the planet to wobble, well, the star to wobble. What are they talking about looking at planets? It causes the star to wobble slightly. This wobble causes a slight apparent shift called the Doppler effect in the frequency of the electromagnetic waves given off by the star. There you go. It causes the star to wobble. That's a typo, not the planet. And so, yeah, the star does this wobble. It shifts from the red to the blue section, which is the Doppler effect, and we're able to see it. The Doppler effect is also how we know about the Big Bang, because we see all the stars moving away from us, so they're shifted towards the red end of the spectrum, which makes us know that the Big Bang is a thing. How do solar nebula and planetary nebula differ? So I think that is going to be back on the other page. Where's my pen? So solar nebula, I believe, comes from a supernova, and a planetary nebula just comes from a red giant. Yeah, that's going to be the proper answer. Let's see if it lets me show it. So if you scan through this, you should see something about a planetary nebula, which comes from a red giant. Do they talk about a solar nebula? But that should be enough to get you to the actual answer. There's a solar nebula. A solar nebula, here it is. Solar nebula and planetary nebula differ in that the solar nebula are clouds of gas and dust through the form of solar systems, whereas the planetary nebula are clouds of gas and dust that form when matter is ejected from a dying star. So I actually had that backward. The solar nebula is just like a dust cloud in the system. The planetary nebula comes from a supernova of a dying star. When a star dies, it results in a supernova. Oh, when star A dies, it results from a supernova. When star B dies, it results in a white dwarf. Which of the following inferences is most likely true? I can actually show you this image from my dual credit PowerPoint, which shows it better. Hold on, it's right here. So this is going to show you small stars versus big stars. If it's a big star, it will explode into a supernova. So star A explodes into a supernova. Star B results in a white dwarf. So that should tell you something about the size of the stars. Star A is more than likely bigger. Star B is more than likely smaller. So that should help you through most of the questions. If you have any questions, please let me know. Nice. I need to get rid of this. So thank you for tuning in, people at home. Remember to like and subscribe and maybe play Roblox.